Hello everyone. Today we are going to see the concepts about hyperspectral remote sensing. This topic is closely linked with multispectral remote sensing. We will look further into the concepts of this. So basically it is an advanced technology in remote sensing because the basic technology what we consider is multispectral, uh, that is remote sensing in multiple spectral bands. Hyperspectral, when it comes to hyperspectrals, hyper literally means is excessive and spectral means is excessive spectral bands. So this is an advanced technology which came later after multispectral. So basically hyperspectral remote sensing is also called imaging spectroscopy. This is another name of hyperspectral remote sensing. So basically just don't get confused about the names. This is another name. So what it covers basically the concept of spectroscopy. Spectroscopy basically considers that how electromagnetic radiation interacts with matter, and and what the matter will reflect and absorb according to its own property and material. So that measurement of an matter radiating or absorbing radiation is comes under spectroscopy. So basically this imaging spectroscopy is a single system which often includes large data sets and require new processing methods. So when hyperspectral comes into account, it will consider around hundreds of bands. So when hundreds of bands comes into picture, so it will automatically increase the volume of the data set. It involves acquisition of image data in many contiguous spectral bands and ultimately producing laboratory quality reference spectra for each pixel in an image. So it is basically saying this is an image, and it will contain different multiple spectral bands like a stack, and one pixel will give you around 100 values. If there are 100 bands, one pixel will have 100 values. So basically one pixel will give a very good reflectance spectra, or it will give many values for the spectra in different spectrum parts of EMR. So as I earlier said, it almost contains from 100 to 200 bands. As in when we talk about multispectral, it will contain up to 15 or 16 bands. So up to 15 or 16 bands, it is multispectral, and mostly whenever it goes above 16, so it will come under hyperspectral. So what the main difference is, hyperspectral remote sensing must contain at least 16 bands, because without 16 bands or a lower number than 16 will always give multispectral remote sensing. It will not be a topic of hyperspectral. So why this hyperspectral was needed? Why so many bands were needed? Why multispectral remote sensing was not enough for some things or some applications? So yes, definitely hyperspectral was found to be very informative in in mineralogy, or we can say in terms of mineral mapping. So whenever we talk about geological aspects, or in terms about geology or studying the earth surface, so whenever mineral mapping is required, so hyperspectral works very efficiently, and it works better because it helps in mineral identification in different electromagnetic spectrums, as different minerals and different elements will reflect in different spectra. So in geology it helps very much in mineral mapping and mineral spectra identification. It also helps in terrestrial vegetation in understanding different types of vegetation, as we have already known. Like we have agriculturally we study the vegetation, we for urban grasslands we also study the vegetation, for forestry we also see the vegetation. So vegetation also have this broad scope where we require multiple spectra to essentially study about it, and also about man-made materials, whatever man-made materials are, and what chemicals and substantive man-made materials have. So that identification is also done through hyperspectral. So this image gives a very clear picture. Like you can see this, if we have one band of an image, it will give to panchromatic. If we have tens of bands, okay, and like up to 16, it will come under multispectral. And if it is hundreds, as you can say, see, like this is an image, and this is the spectral variation, number of bands. Here it's 10, here it's 1, and here it's 100. So it is called hyperspectral. Here one thing to observe is, if you can see, panchromatic band only covers a range of electromagnetic spectrum. Multispectral will cover discrete wavelength regions. So whenever the difference comes, is this is discrete, but whenever you observe hyperspectral, it will give continuous spectra, continuous, or we can say contiguous, whichever term you use. So multispectral covers multiple wavelength regions, but they can be connected or they might not be connected. We can have the spectral gaps here, but this is not the case in hyperspectral. So one more thing which deviates is hyperspectral might carry broad bands. Like you can see, this is a broad band, this band starts from here and ends here, this is a very broad band, but hyperspectral will contain very fine narrow bands, very fine narrow bands, as you can see here, very fine narrow bands that will compose of. So basically two major thing is multispectral and hyperspectral is, this will carry narrow bands, this will carry broad bands. This will create give continuous spectrum, and this will give discrete spectrum. And panchromatic have a very different application. We can talk about this later. So now it comes upon understanding about why hyperspectral data sets is as what we see in the real world today and how it came existence. So basically, if you can see this is a data cube, which we understand if we have an image, okay, if we have an image, the data inside it, basically what it will give. So basically this XY plane will cover the spatial information overall of the image, but overall this Z direction in the data cube, this Z direction will totally give the width, and this width is basically the number of bands it will have. So that Z direction will always give the spectral information, and spatial information is in XY plane. So that's why it is covering that there is a spatial data of around this 1024 by 614. This is a image size, and it have a 3 band color composite image. R value is this, G value is this, and B is this. But the Z value, which is the number of spectral bands, this is 224 contiguous bands, and the range is 0.4 micrometer to 2.5 micrometer. So these both things will define the spectral resolution of the sensor. Spectral resolution. So the number of bands is 224, but the range is basically 0.5 micrometer to 2.55 micrometer. So basically what we see in hyperspectral remote sensing is the range is in visible and infrared region. This is a very important concept to notice, that hyperspectral remote sensing won't go beyond infrared and before visible. So the majority of the hyperspectral sensors will work in visible infrared region. So you can see this visible is started, and this will cover entire range of most of the range of hyperspectral infrared. Okay, so visible infrared will be the range for hyperspectral remote sensing studies. So this is basically an example of Everest, which is a sensor of a hyperspectral sensor covering of 224 bands. So this is the same thing which I have already talked about. So this is saying the Z axis is made up of all the other bands as if they were stacked like a ream of paper and placed on its side. So it's like we can see a stack of paper or a ream of paper, just showing about how the spectral bands are arranged. Okay, and the H pixel will give around the Z axis if we calculate. So it is saying just this is the H pixel, this is the H pixel, and from here when we see in the Z direction, it will give about the enormous amount of information contained in the spectra. So basically all the details of the spectral information we will have from this. So the number of bands in Z direction because it is hyper spectral, but it also depends on the instrument, but basically it should be 100 or greater, because some of the sensors will have 100 bands, some will have 150. Hyperion sensor will have 220 bands. The Everest watch we saw last is 224 bands. Some sensors are more than that, maybe 300 bands. And some of the I have seen one two sensors like around 75 bands. If you say 75 bands, this is also hyperspectral. There is an Indian IMS Hyperion hyperspectral sensor, that is a hyperspectral imager, IMS, that is Indian Mini Satellite Hyperspectral Imager, that is an Indian hyperspectral sensor, the only Indian hyperspectral that was also on Chandrayaan mission to study the surface of moon. This sensor was developed by India, and it contains 64 bands, 64 bands totally in visible and near infrared region. So this 64 bands will also give the hyperspectral information. So this is a hyperspectral sensor. Okay, so each pixel whatever we get will give each the spectral signature with the associated wavelength related to in which it is captured. Like this 64 bands, in all the 64 bands, they all will give around 64 spectral signatures in each of the wavelength portions they are covering in. So it is clear, like hyper means excessive, so and imaging means when we get the when we measure the radiation or the spectra in terms of image. Okay, so spectroscopy basically measures in values, but when we term uses imaging, so it will give the output as an image. And hyperspectral, this is a condition at least 16 bands hone chahiye, and then it will also give you contiguous bands. This is also a, if you have 16 continuous bands, it can be multispectral, but because it is continuous with 16, this can also be taken as hyperspectral. So that will be the thing. You should be very clear with what are spectral signatures, what is electromagnetic radiation, and how this electromagnetic radiation, basically what parts are used in remote sensing and various applications, and which spectrum is used in which application. You should always be aware of that. So whenever we talk about instruments like meter comes up, so whenever we talk about radiometer, it will measure the intensity of the electromagnetic radiation. The radiation measurement, radiometer, intensity of the electromagnetic is measured. When we talk about spectrometer, so basically it will collect the spectral distribution of EMR. These terms are very important. So when we see here working principle, as you can see, for the same region, for different regions, same number of spectral bands are giving various outputs in different bands. So each pixel contains a sample spectrum that is used to identify the materials present in the pixel by their reflectance. So for example, per pixel is giving the can give the reflectance in a part can be covered with soil. If we talk about the pixel only, some part of the pixel will give the soil signature, one will give the water, and one will give the vegetation. As we know, vegetation reflects very well in infrared region, and some part is reflected in green region. Water is reflected very nicely in infrared region, and soil is very good reflected in a short wave infrared region, that is SWIR. So due to different wavelength bands, we can capture these information very distinctively. So very clear information we will get out of all the bands we are using. If we just have used infrared band, which should have covered short wave infrared and near wave infrared, so maybe we could not have distinguished soil and water properly. But due to this different narrow regions of wavelengths, we get a clear reflectance picture. We get the clear signal. We get a clear signal actually. So that is a very advantage of this kind of data set. as you can see. So basically what is the goal of hyperspectral remote sensing is to obtain the spectrum for each pixel in the image of the scene with the purpose of finding the objects, identifying the material or detecting the processes that what's going on. As we have already talked about geology process. Spectroscopy I have already talked about. It will basically measure the individual absorption at atomic level. Basically it will measure the individual absorption at the various atomic level, that how electron behaves when an electromagnetic radiation will strike with it. The atomic structure will depend on what kind of matter it is. It will give different measurements in solid, liquids and gas. And whatever we when we focus on the earth, when we basically talk about earth, we will call it imaging spectroscopy, because we are not dealing here with physics or chemistry things, but we are definitely dealing with remote sensing. So we will be considering only the earth surface, and that's why we will be calling taking the in account the imaging spectroscopy rather than spectroscopy. So hyperspectral remote sensing, the concept came in mid 80s, and it was widely used for mapping of the minerals. I have earlier said by the geologists, as in rocky areas it was very easy to identify what kind of minerals and elements were present. As we have known that if a rock is there, it might contain some portion of calcium, it might contain some portion of potassium, maybe not, or it may contain carbonates, or it may contain other type of metallic compounds like carbon basically. So it all depends that different elements are identified with this help. So goal is basically identification and finding of the objects, mapping of the minerals. So it is all it's dependent upon spectral coverage, spectral resolution, signal to noise ratio of the spectrometer. The instrument quality is also taken into account, abundance of the material and the strength of absorption features of the material in the wavelength region measured. As I have earlier said, this is the same thing. Multispectral will cover 5 to 10 bands of relatively large bandwidths, but hyperspectral will cover 100 to 200 narrow bandwidths. Yeah. Applications are various: atomic, atmosphere, ecology, geology, coastal waters, snow and ice, biomass burning, in commercial applications as well. You can have a look. And I think this is all for today. I will continue in the next section. Thank you so much for joining in, and please do let me know if you are okay with this, so I can upload more videos like that. Thank you.